Your phone knows exactly where you are, down to half a meter. But how does a satellite 30,000 kilometers above Earth pinpoint your exact location? The answer is pure, beautiful physics, and it works right now, even as you read this. Welcome to the most precise engineering achievement invisible to the human eye. Today, we dissect the GPS system, from orbit to sentiment. GPS, the Global Positioning System, was built by the United States Department of Defense in the 1970s. Originally designed for nuclear missile guidance, it was later opened to the entire world. Today, the GPS constellation consists of at least 31 operational satellites circling Earth. These GPS satellites orbit at an altitude of approximately 20,200 kilometers above the surface. At that altitude, each GPS satellite completes 2 full orbits every single day. The GPS satellites are arranged in 6 orbital planes, tilted at 55 degrees to the equator. This clever GPS satellite arrangement guarantees that at least 4 satellites are visible from any point on Earth at any time. Each GPS satellite broadcasts a continuous radio signal traveling at the speed of light. That GPS radio signal carries 2 critical pieces of data: who sent it, and exactly when it was sent. Your GPS receiver captures these signals and calculates how long each signal took to arrive. The speed of that GPS signal is exactly 299,792 kilometers per second. Multiply the travel time by the speed of light, and you get the exact distance to that GPS satellite. This fundamental GPS method is called time-of-flight ranging, elegant, simple, and terrifyingly accurate. One GPS satellite gives you a sphere of possible positions with you somewhere on its surface. 2 GPS satellites narrow it to a circle, the intersection of 2 spheres. A third GPS satellite reduces the possible positions to just 2 points in 3-dimensional space. One of those 2 GPS points is floating absurdly in outer space, so your receiver discards it instantly. 3 GPS satellites are mathematically enough to find your position on Earth's surface. But GPS systems always use a 4th satellite, and here is where it gets brilliant. The 4th GPS satellite solves the clock error problem, a tiny error that would otherwise ruin everything. Inside every GPS satellite sits an atomic clock, one of the most precise instruments ever built. A GPS atomic clock loses only 1 second every 300 million years. The atomic clock oscillates using cesium or rubidium atoms vibrating at billions of cycles per second. Each GPS satellite carries multiple atomic clocks as redundant backup systems. Without atomic clock precision, GPS positioning errors would balloon to over 10 kilometers. Even a microsecond of atomic clock error translates to 300 meters of positioning error. Here is the part most people never know: GPS would break without Einstein's theory of relativity. Special relativity says moving clocks run slower. GPS satellites move at 14,000 kilometers per hour. Special relativity causes GPS satellite clocks to tick 7 microseconds slower per day than ground clocks. General relativity says clocks in weaker gravity tick faster. GPS satellites are far from Earth's gravity. General relativity adds 45 microseconds per day. GPS satellites gain time instead of losing it. Net result: GPS satellite clocks gain 38 microseconds every single day without correction. Without relativistic GPS correction, your GPS navigation would drift 11 kilometers every single day. GPS engineers pre-adjusted the atomic clock frequency before launch to compensate for relativistic drift. Einstein's equations are literally baked into every GPS chip on every smartphone on the planet. Even with atomic clocks, GPS signals face 4 main sources of error on their journey to you. Error number 1, the ionosphere, a layer of charged particles that bends and slows GPS signals. The ionosphere GPS error can add up to 30 meters of uncertainty to your position. Error number 2, the troposphere, water vapor in the lower atmosphere refracts GPS radio waves. Error number 3, multipath, GPS signals bouncing off buildings and terrain before reaching your receiver. Error number 4, ephemeris drift, tiny orbital position errors in the GPS satellite itself. GPS engineers developed a powerful error correction technique called differential GPS, or DGPS. DGPS places fixed ground reference stations at precisely known GPS coordinates around the world. These DGPS ground stations measure the GPS error in real time and broadcast correction signals. Your GPS receiver applies those DGPS corrections, and suddenly your position accuracy jumps from meters to centimeters. The gold standard of GPS precision is called RTK, real-time kinematic positioning. RTK GPS uses the carrier wave phase of the GPS signal, not just the GPS code timing. The GPS carrier wave has a wavelength of only 19 centimeters, far more detail than the GPS code. RTK GPS measures fractions of that 19 centimeter GPS carrier wave, down to 2 centimeters. RTK GPS requires a base station and a rover unit communicating in real time over radio or internet. The RTK GPS base station knows its own position with millimeter accuracy and streams live GPS corrections. The RTK GPS rover receives those corrections and resolves the carrier wave phase ambiguity through complex algorithms. Within seconds, RTK GPS achieves 1 to 2 centimeters of horizontal accuracy, anywhere on Earth. Let us now tear down the GPS satellite itself. What lives inside that metal box in orbit? The GPS satellite body is roughly the size of a large refrigerator, about 2 meters long. The GPS satellite unfolds massive solar panels spanning nearly 9 meters to power its systems. Inside the GPS satellite, the atomic clock module is the most critical and most expensive component. The GPS satellite transmitter broadcasts its L1 and L2 signals at 1575 and 1227 MHz respectively. Modern GPS satellites also broadcast L5 signals, a newer, more robust civilian GPS frequency. Using 2 GPS frequencies simultaneously allows receivers to calculate and cancel ionospheric delay in real time. The GPS satellite also carries thrusters that fire occasionally to maintain its precise orbital GPS position. The GPS satellite ground control network monitors every satellite around the clock from stations on multiple continents. The most obvious GPS application is navigation, but centimeter GPS enables something far more dramatic. Precision agriculture GPS systems guide autonomous tractors to within 2 centimeters across entire fields. These precision GPS farming systems optimize seed planting and fertilizer distribution down to individual centimeter rows. Autonomous vehicle GPS systems use RTK correction data to navigate streets with surgical GPS precision. Civil engineering GPS survey teams use RTK GPS to measure land boundaries to millimeter precision. The financial world relies on GPS timestamp signals to synchronize global stock exchange transactions. Power grid GPS synchronization keeps electrical networks stable across entire continents using GPS timing. Seismologists use GPS displacement sensors to detect millimeter-scale ground movement before major earthquakes. Drone delivery GPS systems must maintain centimeter positioning to land payloads precisely on target platforms. GPS is not alone anymore. Europe built Galileo, Russia built GLONASS, China built Beidou. A modern GPS receiver uses all 4 satellite constellations simultaneously for maximum accuracy and redundancy. GPS-3 satellites, the newest generation, deliver 3 times the accuracy of older GPS satellites. Future GPS systems aim for sub-centimeter positioning available on standard consumer smartphones. Indoor positioning, GPS's great weakness, is being solved by fusing GPS with Wi-Fi, UWB, and LiDAR. Quantum GPS sensors under development could make atomic clocks obsolete by using atom interferometry. Think about this: every time you drop a GPS pin, 31 satellites, atomic clocks, and Einstein's equations work together. All of that GPS complexity, all of that physics, completes in under 1 second. The GPS system is perhaps the greatest invisible infrastructure humanity has ever constructed. If GPS satellites were suddenly switched off, global aviation, shipping, banking, and communications would collapse within hours. Next time you navigate with your GPS phone, remember, you are holding the product of 60 years of physics and engineering genius. If this GPS breakdown blew your mind, subscribe, because we have more invisible engineering waiting to be dissected.